Welcome back to this course on linear algebra. As you know that last lectures I have been talking about the concepts of generating systems, linear independence and basis. This lecture I will introduce a concept of dimension, and we will prove that every vector space has a basis and any two bases have the same cardinality, and this common cardinality will be called the dimension of a vector space. So, let me do it first. As usual, K is an arbitrary field and V is a K vector space. And as a first step, we will assume first that V has a finite generating system. This we will make this assumption for today's lecture, and maybe the next lecture we will deal with arbitrary vector spaces. So, first I want to prove that V has a basis and V has any two bases have the same number of elements. So, you note that from the last lectures we note that if V has a finite generating system, then every other generating system will contain a finite generating system. Then I will just note it here, this will be used again and again. Every other generating system of V will contain a finite generating system. Let me recall the proof of this very quickly. So, we have given V as some finite generating system. So, let Vi I in I be a finite generating system for V, and let Xj j in j be an arbitrary generating system. For V. Vi is a finite generating system, in this I set is finite set, and this j could be finite, j could be infinite, but we want to extract a subfamily from Xj which generate V. Well, okay, so it is a generating system. So, now let us, this is a generating system means every vector in V is a linear combination of these Xj's. So, in particular these Vi's. So, for each I in I, Vi has a representation in terms of this Xj. So, that is A I j Xj, j in j, and where this A I j tuple j is varying here, this should be in k power round bracket I, round bracket j. Please recall the notation, upper round bracket j means only these Aij's are almost all 0 for all j in j for a fixed I is fixed. So, now it is clear that if I take the subset j prime consists of all those j in j such that a prime not a prime, all those j in j such that aij is non-zero for some I. This is a subset of J and it is clearly finite subset of J. Because if you fix an index I, then only finitely many aij's are non-zero. So, I am putting it all. So, it is clearly finite, and also what is clear is how do I go next? I am not able to go next page.
I insert new page.
Insert. It is stuck. Okay. Oh. Okay. Sorry.
Yes, sir.
Okay. Okay. So, this J prime is a finite subset of J, and also it is clear that all these VI's I in I belongs to the subspace generated by xj where j is varying in j prime. So, that means k vi subspace generated by vi is, which is the whole V, because vi is the generating system. This is contained in the subspace kxj, j in j prime. When this subspace has a generating system, finite generating system, which is generated by a finite system xj as j varying in j prime. So, that means it should be equality here, because this is a subspace of V, but this is already V. So, altogether we conclude is subspace generated by kxj as j varies in j prime is the whole V. So, that precisely means that is xj j in j prime is a finite generating system for V. So, we have justified our claim saying that if V has a finite generating system, then every other generating system will contain a finite generating system. And now also last time we saw that, which again I recall for the sake of completeness, recall that we have seen that we call, first of all let us recall the definition, we say that a generating system Vi I in I of V is called, or we say that a generating system is minimal if for every I in I, if I omit Vi from this family, it will not be a generating system. V j is in I minus this is I, is not a generating system. For V. So, we cannot afford to drop any vector from this generating system, that is a minimal one. Similarly, we will say that a family Vi is a maximal linearly independent family in V if we cannot enlarge Vi to a bigger linearly independent family. If Vi I in I cannot be enlarged to a linearly independent family in V. In particular, we cannot add one vector in Vi family, Vi I in I, union some other vector V, where V is not any Vi, is linearly dependent over K. So, and also now it is very easy to see that I will just note in the form of theorem. Let V be a K vector space and Vi I in I be a family in V, then the following are equivalent. I will use this TFAE as a short form for the following are equivalent. Number 1, Vi I in I is a basis, is a K basis of V. 2, Vi I in I is a minimal generating system for V. And number 3, Vi in I is a maximal linearly independent family in V. The equivalence of this is really very easy and I want to skip the proof. So, proof I will just say easy to verify. By using definitions. So, our assumptions, remember what we are assuming is V as a finite generating system. That means, if you have V has a generating system Vi, I in I with I finite. Of course, one could also take I equal to 1 to n and write, instead of writing Vi, I in I, V1 to Vn, but there is no harm in writing a general index. So, this is our assumption. Now, the earlier theorem to prove that, so let me write this as a theorem. Theorem, this is what we want to prove. Theorem with this assumption V as a basis. Proof. So, I start with this finite generating system. There are only finitely many elements in this family. So, I check that whether some vectors are needed in this family or not. That means whether vector is a linear combination of the remaining other ones. If it is so, then I will remove it from this family. And continuing this process, we will arrive at a family which is a minimal generating system. And this is possible because this I is a finite set. We are only doing finitely many steps. So, proof is very simple. By removing vectors in this family Vi, which are linear combinations of the remaining ones, remaining vectors, successively we will arrive at a minimal generating system which is contained in this family Vi. And as we saw earlier theorem, that minimal generating system is a basis. So, this is clearly a basis of V by earlier theorem. Note that this process terminates because I is a finite set. So, in finitely many steps we will arrive at a basis. However, we cannot do such a process for infinite set in general. So, we will have to use some more stronger form of set theory to prove these things, which we will postpone till next time. But now our main problem is to show that, now we will show that if Vi, I in I and Wj, j in j are two k bases of V, then cardinality of I equal to cardinality of j. And note that both I and j are finite, because we are assuming a generating system, V as a generating system which has finitely many elements, and therefore, any other generating systems will also have subsystems which are generating system, finite generating systems. So, we could concentrate on finite generating. So, V as a finite basis. So, all bases of V are finite. So, and we want to prove that now any two bases have the same number of cardinality. So, we will prepare for this. So, first I will prove a lemma. So that is a very important lemma for many purposes. This is called exchange lemma. So let V be a k vector space and with basis, now I will color V1 to Vn. And let W be another vector in V. So definitely, because V1 to Vn is the basis, this W we can write uniquely as, with W I can write uniquely as A1 V1 plus dot 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 AK Vk plus An Vn with unique A1 An in scalars, and if W is non-zero, some scalar has to be non-zero, otherwise W itself will be 0 vector, and we will assume AK is a non-zero. So that means this Vk occurs in the expression of W. Then V1 to Vk minus 1, and I want to drop Vk from this basis, and instead of Vk I want to replace by W. So I am exchanging the vector Vk in the basis with the vector W, and I want to claim then this is a k basis of V, and we shall make repeated use of this lemma. First let us prove this lemma. So we want to prove this V1 to Vk minus 1 W Vk plus 1 Vn is a basis. So that means we need to check two things. We want to check that they are linearly independent and it also generates. So first let us prove that they are linearly independent. Proof 1, V1 to Vk minus 1 comma W Vk plus 1 to Vn, this is linearly independent over K. So to prove this, let us assume some linear combination of them is 0, and then we need to conclude that all coefficients are 0. So suppose B1 V1 plus Bk minus 1 Vk minus 1 plus Bw plus Bk plus 1 Vk plus 1 etc. plus Bn Vn is 0, where B1 Bk minus 1 Bk plus 1 Bn, these are the scalars, and now we want to conclude all P's are 0. Well, we have a expression for W in terms of V1 to Vn, we will plug it in here and compare the coefficients of V1, V2 etc. Vn to be 0, because it is a basis. If a combination is 0, then each coefficient must be 0. So replace W by its expression, unique expression A1 V1 plus AK Vk plus An Vn in the above linear equation, and compare coefficients of V1, V2 etc. up to Vn. What do you get? Let us see. So, first the coefficient of V1. So, if you put W equal to A1 V1, then the coefficient of V1 will be B1 plus BA1. This is the coefficient of V1. This is so coefficient of V1 is this, which should be 0 because the combination is 0 and V1 to Vn is the basis. Coefficient of V2 is B2 plus BA2, that is also 0. This will go on till that AK minus 1. So, BK minus 1 plus B times AK minus 1 is 0. This is coefficient of Vk minus 1. Coefficient of Vk will be B times AK. This is also 0. And then again Vk plus onwards, same like V1 to Vk minus 1, that is Bk plus 1 plus B times AK plus 1, this is 0, and so on. Coefficient of Vn will be Bn plus Ban is 0. This is n. Now, from here we want to conclude all B i's are 0 and B is also 0. But look at this kth equation, that will tell you B is 0, since AK is non-zero and K is a field. That is why field is very important, because the product of elements is 0, so and one of them is non-zero, so the other must be 0. Now, B is 0, once you go to B is 0, then look at the first equation, this part is 0. So, B1 is 0. Second equation, B is 0, so this is 0. K minus 1 is the equation, this is 0, so Bk minus 1 is 0. K plus 1 is the equation, this is 0, so Bk plus 1 is 0, and this is 0. So, we conclude all B1, B2, Bk minus 1 are 0 and B is 0. So, therefore, from this we have concluded B1 equal to B2 etc. equal to Bk minus 1, they are all 0, and similarly Bk plus 1, Bk plus 2 etc. up to Bn, they are all 0. So, that proves a linear independence of V1 to Vk minus 1, W, Vk plus 1 to Vn. So, now second part we have to check that V1 to Vk minus 1, W, Vk plus 1 to Vn is a generating system. For V. So, this is also very easy, because we know that V1 to Vk minus 1 and Vk plus 1, this is a basis that was given to you. In particular, it is a generating system. For V. So, to show that this along with W it is a generating system, I only have to check that the vector Vk is a combination of V1 to Vk minus 1, W, Vk plus 1 and Vn. So, to check this, so it is enough to check that the vector Vk belongs to the subspace generated by Vi, I is from 1 to k minus 1 plus kw plus k I is from k plus 1 to n k vi. So, we have to check that this vector Vk has a representation in terms of V1 to Vk minus 1 W and Vk plus 1 to Vn. So, that is very easy because W has a combination like this A1 V1 etc., that is our assumption. This was given to us. And this AK coefficient is non-zero. So, I will keep this term on one side and remaining terms I will shift it on the other side and multiply by AK inverse. So, multiplying by AK inverse, that is possible because K is a field. So, AK inverse exists because AK is non-zero, and I can rearrange this and rewrite it as. So, I will get an equation Vk will be equal to AK inverse W minus AK inverse A1 V1 plus AK minus 1 Vk minus 1 plus AK plus 1 Vk plus 1 plus AN Vn. So, this gives an expression for Vk in terms of V1 to Vk minus 1 W and Vk plus 1 to Vn. So, that proves that V1 to Vk minus 1 W Vk plus 1 to Vn is a generating system for V. So, we will make a short break and do it after the break.